I'm recording and recording. Okay, so last time we we we talked about the word vec, how to calculate the word vec for words automatically. And first we talked about the meaning of the word representation, vector representation of the words. Then we talked about how we find the vectors for each word, and we were talking about it, and we said that the algorithm word2vec is not the only way to calculate those vectors. There are other ways of doing it, and today I am going to look at the other ways of doing those, obtaining those vectors. They have some advantages and disadvantages, and we are going to see it. And then maybe most of you noticed it. I assigned your homework, the first homework. We will talk about your homework, and we will talk about how we are going to do some of the steps of your homework. Okay. Any question from last week? Any questions from the previous weeks? Okay, if there are no questions, so another way of actually calculating the word vectors is the counting the co-occurrences. Let's say I have two words, for example, ice and water, okay? Two words usually, they appear together in the sentences. They are very close by most of the time. Sometimes they appear by themselves, but most of the time they are related. If I count the number of co-occurrences of those words, that means that I am getting statistics about them. And whatever I assign as vectors to those words should be similar to each other because they are appearing together, right? So we are going to set up a window around each word. For example, let's say if I say ice is a form of water. If I take this sentence, let's say I take this word, center word, this one, and let's say my window is this much. This is my W window. So my window is the width of my window is 1, 2, 3, 4, 5. Okay, window of 5. I am looking at in the window of 5 previous words, and I see that water is seen with the word ice. Also, it is seen with the word is, a, form, of. Okay, all of these words occur together in this sentence. And if I keep the statistics, for all the words in my data set, then I can come up with something, and I'm going to show you some examples. Let's look at this very small data set, corpora, very small corpora. Okay, so I have just 3. You guys are hearing me, our online audience? Do you guys?
Yes, sir, we can hear you.
Okay, good, thank you. So I have just these 3 sentences, and I like to use a window of length 1. That means that I will just take these 2 words, or these 2 words, or these 2 words. So just these are my windows. I am just scanning all the data set using a window of length 1. Okay, more common is 5 to 10, but for this example, it's a very simple example. I am doing it that way, and I am going to come up with this co-occurrence matrix, and this is what I am coming up with. Okay. Obviously, if the previous words or the afterwards is not important, or I mean, if that word has happened before me or after me is not important, this matrix is going to be a symmetric matrix. Okay, and I and like occur 2 times, I think, like here and there, right? I and like and I occur 2 times. As I said, this is a symmetric matrix around this axis. Upper part and lower part are the same, symmetric. Okay, so this is a co-occurrence matrix, And it's a natural way to come up with a vector for a word. For example, my vector for I becomes 0, 2, 1, 0, 0, 0, 0, 0, right? You might say that, well, this may not work very well, but I mean, this is a co-occurrence matrix, and if you do it for the whole dictionary, what would be the size of this matrix for the whole dictionary? In Turkish, we have 40,000 words, but usually for these kind of matrices, even if you consider all the forms of Turkish words, it's going to be 500,000 by 500,000, even more than that. So it's going to be a very large matrix, right? And most of the time, most of the entries will be 0, because there are many words that don't happen together. Okay, there are many words that don't happen together. For example, of and I. You wouldn't say them together one after another, especially if the word window is 1. Anyway, so this is going to be a very sparse matrix, but it's going to be a very large matrix. And again, like previously, each word will have a vector of size 500,000, and which we don't like. We don't like this kind of vector. So we have to do something about it. But again, what I am saying here is we don't have to use word2vec to get the vectors. There are other ways of doing it, again, with some advantages and disadvantages. Okay. So the problem with the co-occurrence matrix, as I said before, increase in the size with vocabulary. If the vocabulary is large, my table size becomes larger. Maybe I can manage it, but if the vector sizes are large, then that makes it very difficult to use, very high dimensionality. Okay, and subsequent classification models have sparsity issues because, as I said, many zeros. I don't like them in my vectors and in the matrix. Okay, so models are less robust. What do you mean say that? I mean, if I use a vector to calculate something, a word vector using co-occurrence vectors, to calculate something, to estimate something, the results are not that good. It's not as good as the word-to-vector results. By the way, I did not show you any examples of how to use the word vectors in real life situations, but any machine learning model, any machine learning technique that uses data as an input and that uses output as labels can be used with the word vectors. Yes.
How about if we have a lot of zeros? How about methods like PCA that kind of?
You mean the word dimensionality is so high we should do something about it?
Yes.
Yeah, we are going to look at it in a few minutes. Okay. Did everybody sign the attendance sheet? Okay, good. So we are going to look at that one. Okay. This is what you mean. Okay. Low dimensional vectors. How do you get the low dimensional vectors from out of 100,000 to 100,000 dimensional vectors? Okay. How to reduce the dimensionality? As Uzama said, maybe we can use a principal component analysis. PCA is one way of doing it. Okay, this principal component analysis, if you have a let's say 100,000 dimensional space, you have 100,000 dimensional space, many data represented in space. If you do this analysis, you will transform your space to another 100,000 dimensional space. So I didn't gain anything yet. But the thing is that the first dimension, second dimension, and third dimension, okay, your dimensions are ordered in a way that your top dimensions, most important dimensions in a way, you could say this, your most important dimensions are at the beginning. So Dimensions, the importance of your dimensions in this original space, I don't know. But in this space, you know the importance of those dimensions. So if you say that I am going to take only the first 100 dimensions and I am going to ignore the rest, then it works very well for many applications. PCA is something like that. And today I'm not going to use the PCA directly, but something similar to PCA. Okay. We are going to call it the singular value decomposition. Tekil değerler ayrışımı in Turkish. I'm sure you took the linear algebra course and you have seen singular value decomposition. So the theory says that, the linear algebra theory says that, okay, any matrix, whether it's a rectangular or the square, doesn't matter, any matrix can be decomposed into three components: U component, sigma component, and V component. Okay, singular value decomposition, U and V. Okay, so this sigma component is a diagonal matrix. Only the diagonal elements here are non-zero. Okay, the rest of them are all zero. This U and V, okay, they are orthogonal in themselves. The matrix is orthogonal. What does that mean? That means that if two vectors are orthogonal, this one and this one, their dot product is zero, right? Because if they are orthogonal, their product is zero. Okay, this one is, again, their rows are, because this is a VT, the transpose of T. Okay, these are orthogonal. Okay, this is guaranteed by the singular value decomposition. And if you look at this, these values, these are the singular values. This is guaranteed to be the largest, smaller, smaller. And if you have zero values in this diagonal, it has to be the lower right corner. So zero start from this end, and the number starts getting larger and larger. Okay, if this is a full rank matrix, all the singular values are non-zero. If this is not full rank, then some of the singular values starting from the lower right corner will become zero. That's why to be able to know that if this value is invertible or not, it has to be full rank, right? You just do the singular value decomposition and you just count the number of singular values. Okay, and this column, maybe use a different color. This column, the first singular value and this row are related. This is the most important singular value. This is the most important, you might say, that column, and this one is 2. Okay, so instead of doing the PCA, maybe we can take these vectors. They are all orthogonal to each other, and we can say that, okay, I'm going to use those. So in this case, what did I do? I am saying that if I ignore very small singular values, close to zero singular values, or ignore some of the single values starting from the lower right corner, let's say I am going to take only 100 of them. So the corresponding 100 columns or corresponding 100 rows here are the important ones for me. So that means that I am going to take only the first 100 elements of this U matrix. Okay, maybe this will make sense a little bit. Okay, these are my words. Just a simple Python. Does anybody doesn't know Python in this classroom? I don't know Python. Okay, that's okay. You don't learn Python. Okay, it's a stupid language. You just read it and you write it. You don't learn it. Learning Python doesn't make any difference, because as soon as you learn it, especially for me, I just forget it, but it is easy to read. So what I'm saying here, of course, that doesn't mean that you shouldn't know any other programming languages. You should definitely be very proficient in classical languages like C, C++, Java, C#, etc. So clearly an array, my words, 1, 2, 3, 4, 5, 6, 7, 8, that is a word, okay? So this is a 7 by 7 co-occurrence matrix that I have written with manually. So see, this is a 0, 0, 0, 0, 0. So around this line, it is symmetric matrix, okay? So I added this two-dimensional vector. Its name is x, and I am calling this SVD, singular value decomposition function. This function will return me three matrices U, singular values, and the transpose of V. Okay, and I don't know what that option is. Full matrices false. Well, my matrices may not be full rank. I don't know. I think it is using a different singular value decomposition technique. So after I get this singular value decomposition, this S is a matrix. Well, maybe S is not a matrix. Maybe it's just a vector because it is just singular values. But definitely, U and V are the U and V are the two-dimensional matrices. And if I keep only two dimensions, how many dimensions are there here? This is 1, 2, 3, 7, 8, right? 6, 7, 8. Yeah, 8 by 8 dimensional world. If I do this singular value decomposition again, 8 dimensions. But if I ignore the last 6 dimensions of this U matrix, I wouldn't lose that much information. That's what I am saying according to theory. And if I do this, again, it is easy to understand. For I in range length of words, remember the words is a array of strings. There are 8 of them. Okay, this loop will run from 1 to 8 or 0 to 8, and it says that put this in position U I0 to U I1. This is X position and Y position. So for the word like, okay, for the ith element like, let's say like is element number 0, print this element number 0, which is like, at this position, U, okay, 0, 0, and U, 0, 1. So I am taking just 2 elements of the 8-dimensional vector. So it looks like is here, enjoy, learning, flying, deep, and NLP, and I is here. So you might say that this is not that meaningful. I mean, why deep and NLP are close to each other and like is there and learning? Well, my data set is very, very small. My data set is just these 3 sentences, okay? If I had used hundreds of thousands of sentences, then this would have been more meaningful, but okay, this is algorithm would have been exactly the same thing. So co-occurrence matrix is calculated, do the singular value decomposition and get the 2, 3, okay, this is just, by the way, I am not saying just to use 2-dimensional vectors to represent your words. This is just for visualization. To visualize in 2D world, I can do this, okay? So, again, repeating the same thing. Word2Vec is not the only way of calculating the word vectors. There are other ways of doing it, okay? One of them is co-occurrences, and it is done this way. Maybe it is more logical. I mean, you are just taking the matrix and doing the singular value decomposition, that's it. But there are some certain drawbacks, okay? The problem is this. I mean, he has lots of, I mean, these kind of words happen so much of dot, for example, right? They happen a lot and they kind of dominate the whole statistics, okay? So that happens with all of the other words, okay? So what are we going to do about this? It's going to skew everything up. So maybe do this kind of hack. Okay, you say that I am not going to take anything larger than 100 co-occurrence matrices, okay? If the and some other word is happening more than 100 times, take just 100. Or another, maybe a better solution, just ignore these words, okay? We call them stop words. My battery is dying. Get a new one. Is this the original one? I guess so. So ignore these stop words, and I don't need to calculate the word vectors for these stop words. It will make things faster for me, and it will work, okay? So there are two ways of doing it. Stop words, ignore them, or do this kind of approximation. And many other things. I mean, these guys listed a number of improvements on this co-occurrence matrices. Ramped windows. Okay, ramped windows say that, okay, remember in my example, I use a window of length 1, just the next word or the previous word. If my window is length 10, I need to look at the 10 elements around my center word, but the ones that are closer to me is more important. This one says that, okay, count the closer words more, okay, maybe count them 2 times, maybe 1.2 times, etc. So there are many improvements on top of it. Some of them works very well, some of them we don't know why it works, but it works. Again, don't expect that this technique will work as it is. And if you make it work, if you do this, okay, these are some of the relations that, okay, exactly the same technique. If you draw the positions of the positions of some of the verbs on this two-dimensional world, this is what you are getting, okay? As you see, this is the same word, only their syntactic forms are different, okay? So the root of the word is the same, root of the word is the same, and root of the word is the same, okay? So this is glow catching the syntactic patterns in the vectors. Yes?
This word is mostly occurring in different sentences, how they can be together. I mean, shown and showed is not using the same sentence.
Shown and showed are, well, I mean, they don't appear together, yes, but they appear in places, okay, in places where the others can be used too. For example, I think showed, Americans use this. Shown, British people use it, right?
No.
Some people just opposite.
Showed the past and shown it is the third.
What?
It is shown, it is done. Shown in the past.
The third form of the word.
I think the second form and the third form, but Americans are using the third form for this one too. Anyway, okay, let's say this is the second form and this is the third form of it, and this is the original, and this is the ing form, okay? So instead of using show, sometimes I use showed, okay? I show you this, I showed you this, I have shown you this, I am showing you this, okay? So their co-occurrences with I and this are almost the same, right? So that's why it is expected that they are very similar word vectors, co-occurrences. Okay, when you do the PCA, all the rest gone, and these are, I mean, they don't have the same vector, obviously, because they are different words, but, I mean, the distance between show and showing is much smaller than the distance between show and took or take. Whereas take is there, yeah. Okay, take. That's the important thing. So they are kind of grouped together.
And the algorithm can detect this relationship because of
Algorithm doesn't know what kind of relationship it is detecting. Algorithm only assigns vectors to words. But when we come back and put these words on the board, on the two-dimensional chart, we see that those vectors are very close for the different forms of the same word. Okay, they are very similar. And if you do this for many different words, you get the same effect. So what does that mean? Algorithm, although very simple, it has learned about the syntactic forms or morphological forms of the verbs. Okay, it's very powerful. Okay, so if you are asking a question, show me the if you're asking the question to Google, show me the faces of this classroom, etc. Instead of using that show, if you use showed or shown or showing, it's going to kind of give you the same answer because their vectors are the same or similar. Not same, similar. Okay, and this is not only for the syntactic forms, and it catches these semantic patterns too. This was for the syntax. Okay, this one for the syntax. This one is for the semantic patterns, mana. Okay, in Turkish mana, for example. If you learn and teach, okay, close to each other, okay, driver, swimmer, student, janitor, these are kind of the professions, right? No, okay, these, okay. So these are professions, but these are the verbs, okay? So if I do an SVM, okay, support vector machine classification, does anybody know what a support vector machine is? It's a very simple thing. In support vector machine is this. You say that, let's say in a two-dimensional, it doesn't have to be two-dimensional word, but for the sake of explanation, I am going to do it for two-dimensional word. Let's say, very simple, again. I don't like this example. It's not true, but just it's a stupid example. IQ of a student, intelligent quantity of a student, and the number of hours he is working. How many hours he is working a day. Okay, I would say that if somebody is very smart and is working a lot, okay, probably they will pass, right? Even for some cases, even that guy is not working a lot, but very smart, he's going to pass his courses. So when they started this university, I measured their IQs, and at the end of the semester, I said that this guy passed, this one passed, and these are all passed. But I know that this guy failed, and this guy failed, and this guy failed. Okay, so this is the data that I know from my past experience from last semester. How many students did I have? 5, 10, 11. Okay, I took the data from 11 people. At the end of the semester, I recorded their passing, failing status, and I have this one. Now I am asking my support vector machine to learn this data. Support vector machine does this. It just says that if I draw a line like this, okay, just a simple line. How many parameters do you need to represent a line? Just 2 parameters, right? You will say mx plus b, 2 parameters, 1 and 2. By just choosing these 2 parameters, okay, if now I have somebody new, for example, somebody came and he is here, okay, his IQ is that point and he is working 5 hours a day, I would say that since this blue box is above this line, I expect this guy to pass. Okay, so it's a very simple classifier. Why am I telling you this? Because I can do the same thing here too. Given this data, okay, given this data of the names and the verbs, or the professions or the verbs, I can draw a line like that. Okay, if somebody gives me a new word and tells me, okay, what is this word? Is this a profession or is this a verb? Okay, I can tell you that by looking at this, if it is above this line or below that line. Okay, so, and I am doing this all in an unsupervised way. Why? because I have never assigned any vectors to any of these, right? So, I mean, the real reason why we are using these word vectors is to be able to use these kind of machine learning applications, these kind of machine learning models on our data, okay? So SVM is just a simple model. We are going to use some other machine learning models later. Good? Any questions? Any questions from the audience? Okay, wake him up. The guy next to you. Okay, good. So let's move on. If we like to compare what we have learned last week and to this week, our co-occurrence approach it's very fast for training. It's just you are counting stuff, right? Then doing the PCA is linear, very fast, efficient usage of statistics. I mean, if you have a few number of occurrences, I can take care of that. These are the good things. Okay, the bad things are, okay, primarily used to capture the word similarity, if this word is similar to that one or not. Okay, the other problem is those stop words. Okay, any word that happens a lot in a text, they have more disproportionate importance, and we have. I mean, for the stop words, maybe you can do it, but for some specific text, a word might happen a lot, and even though that word is not a stop word, that will affect our results. On the other hand, okay, our skip-gram or continuous bag of words approach, word-to-vec approach, okay, it is very good in terms of scaling with corpus size. I mean, if my corpus is very, very large, algorithm doesn't change, and it scales very well. The vectors come back very nicely. It doesn't include any PCAs or singular value decomposition stuff. Okay, scales with corpus size, but it is inefficient usage of statistics. You need lots of data actually for this one to work. It doesn't work with small data. Okay. Other nice thing is, okay, it works very well on other tasks, not just for similarity. Okay, it is not just for word similarity. It works very well for the other task, and we are going to see what kind of other tasks we can do, and it can capture complex patterns beyond word similarity. Not just word similarity, but other complex patterns about the meaning, about the syntactic patterns, and etc. And we are going to see some of these later. Okay, good. I did not tell you actually. I mean, I have only shown you this and how to get the vectors out of this. I mean, this one is only looking at the co-occurrences, but we can do better than that. How we can do it? Let's look at this table. Okay. Okay. Given i's around my neighborhood in a sentence, what is the probability of seeing solid? Okay, it is large, right? The probability is large. So you put x in here. That means that if I see i's in a sentence, what is the probability of seeing the word solid around it, right? It is large. For the gas, if I see i's, what is the probability of seeing gas around this word? It is small. If I see i's, well, I mean, this large and small, just bear with me. I mean, this is just examples. You might say that if there is an ice, then maybe somebody is talking about gas too, but this is just an example. If I see an ice, what is the probability of seeing water around it? It's large. And if I see ice, what is the probability of wording a the word random around it is small, right? So I don't see it. And I am going to do the same thing with steam. And again, if I see steam, I know that I saw steam. Seeing solid is small, but gas is large, water is large, and this one is small. So we are going to take the ratio of this one to this one. Okay, it's kind of, I am trying to maybe find the vectoral difference between ice and steam over the solid. Okay, this one is large, this one is small. If you divide them, the result is large. This one is small, large. If you divide it, small. Large, large, it is around 1. Small, small, it is around 1. Okay? So I am trying to relate these two words by looking at a third word. Okay? Ice and steam. I can calculate the co-occurrence of ice and steam. That's fine. But I like to do more than that. I like to look at the co-occurrence of ice and steam over the solid, gas, water, or random. In a way that I like to do something like this. Where should I draw it? Yeah. Okay. Let's say if this is my two-dimensional space, use a different color. Okay. This is ice, and this is steam. Okay, so there is a difference between these two vectors, this much difference. Okay, let's look at some of the words. I would expect solid to be here, right? Solid. And I would expect gas somewhere here. So solid is close to ice but away from steam. So if I do this vector stuff, small and large, but for the gas it is large, it is large and small, and then I have this word random. It is way over here. Random, it is for both of them, it is large and large. Okay, so I am not just trying to determine their positions relative to each other. I am kind of adjusting the positions of the other words, the third word, gas, solid, and random, according to this relationship. This makes it much better. Okay, this makes it much better. Okay, so that's why these ratios are important. Use these ratios to come up with your vectors. The results are going to be much better. So in a way, remember we used to calculate the dot product of those two vectors and try to maximize it. Now we are doing this, okay, between A and B on a third word X. Okay, the difference between A and B. Okay, this is the ratio of the, remember what we are trying to do? Ratio of these co-occurrences over the third word. Okay, which one should be large and which one should be small, in a way that we are trying to come up with these vectors using this idea. Okay, encoding meaning with in vector differences and doing the optimization this way. I am not going to the details, but these are some of the impressive results actually. I mean, take the word frog and find the closest words to frog in my dictionary. Frogs, it is at the top. This is the smaller, closest one. Toad. I know this word, and I think I know this word too. I don't know this word. I don't know this one. I don't know this one. I know this one, and I don't know this one. So how does the globe learn about it? Because it is like it's like the the homework that I assigned to you today, yesterday, whatever. Okay, their corpora, all those words, they come from all kinds of scientific literature. In those scientific literature, these kind of words happen together with frogs, or they can be replaced with the word frog or frogs. Okay. So this is how it works. And coming from the same idea, where is this is exactly the same thing that we are optimizing with the glow. Okay, we say that the difference between man and king, and I expect the queen somewhere around there, right? So we are going to see it in a few minutes. What is my time now? Oh, 16. Are there any questions? I think I am out of my time. I will take 15 minutes of break. Are there any questions? Any questions? Any questions from the team's audience? How many people are there? Okay, not bad. Okay, let's take 10 minutes of break. Let's be here around 14:31. And we will continue from this point. Arkadaşlar oraya isim eklemek yok ya. Kaydolmadınız mı şeye?
Hocam geç kalmışım onu yazmakta.
Oraya isim ben onları almayacağım ki hiç.
Hocam
Ben oradaki yazılıları alacağım.
Yazdım ama çıkmamış.
Yazdın ama git bir daha kontrol et. Hayır yok, ben bunu ne kadar dersten 10 dakika önce bastırdım. Ne zaman yazdın? Derse gelmeden önce.
Ben geçen hafta yazdım ama
Yanlış yere yazdın öyleyse. Doğru haftaya yazdın, emin misin?
kontrol edeyim.
Yani yazdıysan gösterirsen orada hep kayıtlar var. Başkası sildiyse de görürüz. Ya, tamam. Tekrar pilleri değiştim.
Dersin devam zorunluluğu yüzde kaç?
Sınıfta %60 sınıfta olmamızı istiyor. %70 de devam zorunda.
Sağ ol.
Okay, so the question is, how do we know how good the vectors that we produce? We can do this kind of visual inspection. Give me the close by words, and oh, they are looking good, and etc. Or we can do this kind of experiments to see if the results are coming back. Or we can be more systematic. What do we mean by this systematic? We mean where is the rest of the class? Did they leave? They did not come yet. How many signatures I have? One. Okay. Almost the same. Okay, so we can be more systematic, and we can do this. Two types of verification techniques. One is intrinsic, the other one is extrinsic. In the intrinsic evaluation, we just try to see if the vectors are good without using any applications, okay? So it is just intermediate task. It is not a useful task, but it just helps us understand the system, like this word similarity, etc. Extrinsic is better, okay? We evaluate our vectors on the real tasks. What do we mean by real task? For example, we get our vectors and test it on a machine translation system or summarization system, and etc. So if the machine translation system works better with our vectors, that means that our vectors are good. Otherwise, it's not a very good way of producing the vectors. Of course, extrinsic evaluation is more expensive because you need to run applications, right? Intrinsic is easier. And let's look at some of the intrinsic examples. We are trying to do this, okay? I give you the vectors of man and woman, and I will give you the vector of king, okay? Use the relationship between man and woman and apply the same relationship to king to see what I am going to get. And this is the formula. Let's try to read the formula. So in this case, this is A, this is B, and this is C, right? So what does this do? It just, there is a difference operator between A and B. It subtracts man, okay, from woman, and it adds king to it. And you just tell me what we are doing here. What is this? This is a vector, right? And this vector is multiplied by this xi. Vector multiplication means that how similar they are, right? So we are trying to maximize. Find an xi such that it maximizes this expression. But how about this part? What is this part? The denominator. What does this do? It normalizes the vector length, right? It says that I am not interested in vector length. I am interested in vector similarity between these two. Okay, so that will take care of some normalization. So if I run this application man woman, and if I give you these three words, man woman king, and I like you to come up with the fourth one, and I expect it should be close. It should be either queen or something like that, or princess or whatever. Okay, so this is a analogy, word vector analogy example. Okay, so if you are getting somewhere close to queen or somewhere close there, So your vectors are not bad. Of course, this is not to be done only for this example. There are many examples like this. For example, you might say Turkey, Ankara, Greece, and you would expect Athens, right? And you would say Ankara, Çankaya, and Istanbul. What would you get? Çankaya. What?
Fatih?
Maybe is Fatih the where is the governorship is in Istanbul in Fatih? Yeah.
Next to him.
Yeah. So something like that. Ankara, Çinçin Bağları, Istanbul what?
I don't know what's Çinçin Bağları.
What?
I don't know what's Çinçin Bağları.
I am not asking you. That was good enough. What did you say?
Bağcılar.
What?
Bağcılar.
Really? Maybe Gazi Osman Pasha. No. Okay. Just ask this. Okay. Just train your word to vec on knees, media, and see. By the way, they all demolished all the nice gecekondu and Çinçin Bağları. Now they have. It looks like this Fikirtepe thing. They don't have anything left from Çinçin Bağları anymore. All Mamak is gone. I like them better actually, the old forms. Anyway, so it works. It should work. These kind of analogies, and if the analogies are coming back nice, then you would say that okay, these are intrinsically this is working good. Another one, okay, like this one. Brother, sister, nephew, niece, uncle, aunt. Again, you say man, woman, brother, and the question mark. It should come back with sister. Okay. What else? Again, the CEOs of the companies, we know that. These are about meaning, right? These are the meaning of the vectors. These are the semantic relationships. Okay, strong, stronger, and strongest. And they all should be tied together and using these kind of relationships, and superlatives it works. So some people did experiments about that, okay. Analogy evaluation. This SVD is singular value decomposition. So this model is based on SVD. I don't know how they did it, but we are going to compare it with the ones that I told you. So this model SVD small and large. This is continuous bag of words. Remember the word to vec. And this is the skipgram. I showed you the skipgram first and the continuous bag of words. One of them was taking the center word and trying to estimate the context word. The other one takes the context word and try to estimate the center word. Okay, and again we have the glow. Okay, so the dimension of the vectors are 300. Size of the data is 6. What is B? I don't know what B is. Billion bytes? Okay, billion words, okay. So this one says that semantic similarity, syntactic similarity, and total. As you see, SVD is doing very bad. Okay. The best ones come from glow for the semantic. Okay, continuous bag of words for the syntactic, but in total, glow is a little bit better than the other ones. But compared to the other alternative methods, which is 42s and 60s, this is much better. Okay, so it's an evaluation technique using the analogy example that I gave you. So how did they do it? Of course, they come up with these. Okay, maybe 100 of them. Okay, ask the same question for all the methods and try to see which one estimates the best one more accurately. Okay, and in your homework you are going to choose one of these methods to verify your vector representation techniques. The other one is okay. This is another way of looking at the same experiment using the different data. Okay. Again, they are running the same test, but this time they are training on different data. Wikipedia 2010. Okay, 1 billion is 1 billion tokens, 1 billion words, 1.6 billion words. Okay, and there is a gigaword 5, total of 4.3 billion words. And let me make this a little bit bigger. Okay, and this one is large, and this one is common crawl, just crawling the internet and getting lots of data. This is 42 billion tokens, very large one. Okay, so as you see, when the data gets larger, okay, when the data gets larger, the results are becoming better, especially for this giga. Okay, what do you think the real reason is between these two? By the way, this is semantic, this is syntactic, this is overall. Okay, let's look at this one. As you see, the number of words are much larger here than the Wikipedia ones. Why do you think that this is not doing as good as even 1 billion Wikipedia tokens? I mean, between these two, I see the difference, right? This one goes up, this one goes up, and this one goes up. Just a little bit, but 5% difference is not bad. But I don't see the same thing from 1 billion tokens to 4.3 billion tokens, like 4 times more data. I am doing worse. Why do you think the performance is getting worse?
Quality of text.
Maybe it's not as coherent.
Who is talking and what are you saying?
Maybe it's not as coherent as the one in Wikipedia.
Why do I need to deal with the coherency? What do you mean coherent?
It maybe like the stylistically in a written way, maybe it's not.
Well, I mean,
similar to, like,
you saw.
Usually they have strict standards for writing, and how do you have to formulate?
Yeah. Usually with the Wikipedia, some other people review what you have written, right? You don't see any spelling errors in Wikipedia, right? And usually the whatever they are writing there is almost correct. Okay? They don't kind of contradict with each other, at least in the same paragraph, right? And the sentences are right, grammatically okay. Otherwise, other people would fix it. That's why we say that Wikipedia is a better source of producing these kind of words. And if you go even like larger level, common crawl, the numbers are getting a little bit better, okay, compared to Wikipedia of 2010, but it is not that much. I mean, more data doesn't always mean better accuracy, okay? If there is noise in your data, then that will cause problems with the globe. I think these are globe results, yeah.
That's still like 42 billion tokens, so
It's so big, but you don't see that much difference.
it's obfuscated.
What?
Obfuscated. I think using Wikipedia is much better than common.
I don't understand what you are saying. Say it louder.
I'm saying it's obfuscated. Using Wikipedia will probably be much more faster and efficient compared to that.
But this is not about efficiency, this is about accuracy. And accuracy is not going up. That means that there is lots of noise in it. There is lots of contradicting stuff in it. Okay, maybe our algorithm is not good enough to process that kind of data. Anyway, by the way, this is another example. Do the same test using different number of dimensions. You see, I can go from 2 dimensions to up to 500,000 dimensions. Which one is going to do better? And as you see, after some point, it doesn't matter if you have 300 or 600 dimensions, you are going to get the same. There is a marginal difference between this and this in terms of semantic, but overall, so it looks like 300 is the sweet spot. Okay, otherwise, the accuracy that I'm gaining by adding more data is not worth the efficiency issues. Okay, this is analogy. Okay, another intrinsic word vector evaluation is the similarity. This is what you do. Okay, you get 2-3 people, you ask them, how similar is tiger to a cat? Just give me a number between 1 and 10. If you say it is 10, it is the same thing. If it is 1, they are completely dissimilar, etc. So tiger is very similar to tiger, it is the same thing, it is 10. Tiger is similar to cat, so most people said that it is either 7 or 8, right? So that's the kind of the average. How about the similarity between stock and CD? It's very similar. Stock and Jaguar, it is very, very dissimilar. Okay. Professor and doctor, it is similar. Plane and car, it is kind of similar again. So you ask these kind of questions to people, and then you ask the same question to your word vectors. Okay. You take the cosine similarity between them, normalized cosine similarity between them, to see if you are getting the similar results, and you compare your results with the humans. Okay, if you do that, here is your results. Again, single value decomposition, continuous bag of words, etc. What was the difference? Yeah, okay. So these are our 6 billion words, 42 billion, and 100 billion continuous bag of words. It looks like Globe is beating them in many cases, but I don't remember the columns. What are the columns? Columns are the I don't know what the columns are, I forgot. Different implementations, different options for the...
Maybe different data sets?
Well, no, data set is here. Size of the data set is the same data set. I mean, there are 3 data sets, 1, 2, and 3. Okay, I forgot about the column, sorry.
I mean, different tests, because wasn't that LDS the one that they asked humans about? The model.
I think these are different, but how come they can apply it? I forgot, I'm sorry, but the main idea is here. Globe is doing very good in terms of these kind of intrinsic evaluation stuff. But the thing is that Globe doesn't do very well when it comes to extrinsic evaluation, that is, evaluating it under real NLP applications such as translation and the summarization and the question answering. Okay, good. Similar table for the other stuff. Okay, so these 2 examples are for the intrinsic evaluation, analogy and the similarity. Before giving you an example for the real world applications, I like to go back and I like to talk about your homework. How many people read your homework? Homework number 1? Okay, many people did that. Good. Your homework is about, okay, vector representation of words. Okay, this is what you're going to do. You're going to download many textbooks, so it is better than Wikipedia. Okay, these are official Ministry of Education textbooks, and you can download them from this link. This is Açık Öğretim Lisesi, Açık Öğretim Kitapları, etc. So high school books, okay, they are all free. you, for example, geography is a nice one. You download this one. I think it's going to be, why is it so slow? Usually they are more than 100 pages, 125 pages. They are nicely written, and they are all in PDF. Find a way to convert them to text files, standard text files, okay? And if you think it will make your job easier, you may convert all the Turkish characters to English characters too. For example, the characters like yumuşak G, etc. You don't have to use them if you don't want to use them. But using the Unicode stuff, it is easy to use them actually. So I downloaded it now. It is 200 pages. Okay. If I select all the data, I guess I can just, okay, I can just save it. So nicely written sentences. Okay, if you select this and paste it somewhere, but you are going to get this kind of stuff too. For example, under the images, under the images. Is there any question? Under the images, you have the titles, and those titles will go into your text files too. So it will be a little bit noisy because, I mean, it is not easy to get rid of those kind of captions and titles and this kind of stuff, but it will be okay. So you get this first, and I'd like you to where did my, oh, I need to go back. Yeah, okay. So you should have at least 2,000 pages of Turkish text. More is better, of course. And you download this Word2Vec source code from this Mikolow's GitHub page. Compile and run it. It's a C code. Very simple code, like maybe 1,000 lines again. You run it on this page. Okay, and there is a code for running the analogy and similarity test in that program. Okay, you say that give me the similar words to this one, and it gives you the words. Okay, or you run the analogy example again. But the problem with the Word2Vec and the Glow actually, they don't work very well for the Turkish text. Why? Because these kind of vector representations, they take the word itself, and for example, oku and okudum are two Turkish words. Okudum, okumuş, okumuşlar, okumuşlardı. These are all different Turkish words for Word2Vec or Glow, right? So maybe you won't see any occurrences of okumuşlardı in any of the PDF documents in those texts, but I like to know its word representation. So there is a way to do it. I just invented it. Actually, I stole the idea from a paper. So this is what you're going to do. Okay. Find an open source program to divide the Turkish into syllables, heceleri ayırmak. For example, if you are given this Turkish words, okula gitmek, you have, instead of okula gitmek taken as like 2 words, you are going to take it 1, 2, 3, 4, 5 words. O is a word, ku is a word, Allah is a word, git is a word, and mek is a word. Okay, so run your Word2Vec on these syllables. Okay, instead of the word itself. So at the end, you are going to assign vectors to these syllables. So for Turkish, okay, syllables are like one letter syllable A, or 2 letter syllables like LA, or 3 letter syllables like bak, etc. We don't have in Turkish, we don't have 4 letter syllables, but we got stuff like from other languages. You know, Turk is not a Turkish word, right? We have these kind of syllables too. So there are many C code or Python code that does the syllabalization of the Turkish words. Convert all the words into syllables and run word2vec on that. So that means what? For each syllable, how many syllables are there in Turkish language? There are 20. No, there are only 8 of them, right?
Yes.
And this one 8 times 20, something like that, right? How many letters in Turkish?
Shouldn't be 19 because we don't count.
29. 29 minus 8 is 22. 8 times.
But we also remove the yumuşati as well.
Yeah. Well, I'm not assuming that you don't take them out. So 8 times 29 times 2 because you can change the order. It is not much. So all I'm saying is that we are talking about at most, even if you take all the vowels and consonants. So this is 30 times 30 times 30 times 30. 30 to the power 4. Even if you have it for all the 4-letter syllables, but this is over exaggeration. Let's say 430 to the power 3. What is this number? 900 times 30, right?
27,000.
Yeah, that's it. Okay, we are talking about a dictionary size of maybe at most 50,000, not much. So that will give you the vectors for the syllables. But how am I gonna calculate the vector for the whole word? You take, for example, okula. Okay, this is a word, right? Take the word vector for this one, add to the vector of this one, add to the vector of this one, and that will give you the vector for the okula, word okula. Or you are going to get this word, 2 vectors, the vector for git plus the vector for Mac, it will give you the vector for the git Mac, okay? So that way, for any word, you will be able to calculate the vectors. I don't know how this is going to work, okay? If it works good or bad, then your job is to compare the word2vec results. You already run the word2vec results with this one, right? So what are you going to do? Run analogy and similarity experiments for both vector sets for at least 30 Turkish examples, okay? For the analogy and for the similarity too. And of course, you are going to give me those examples yourself. You're not going to find your examples anywhere. You are going to come up with your examples. And you are going to measure your accuracy and using formulas that I showed you a few minutes ago. And you are going to write a nice report, okay? Any programming language is okay. Word2vec source code is a C language, but I mean, if you don't want to use C, but it just you are not going to change Word2vec, right? You are going to change its input. So it's not a very programming heavy homework, but it is intense work, and you will run into some issues, especially your data will become large. I suggest you start from small data, like 1 or 2 textbooks first. Okay, and see what's happening, if this is making any sense or not. Okay, this should work because remember, if okul has a word vector, okay, if lar has another word vector, by adding this, what I am doing is just adding the plurality vector to the stem of the vector, the stem of the vector of the stem, right? So it's kind of whatever the similarity is trying to do. So we are trying to add this vector of plurality to the base vector. So it should kind of work. And actually, this is not my invention. This is the main idea of fast text. What is, okay. Fast text works exactly the same way, but I didn't want you to implement this fast text technique. It will be involved, it will be detailed. So instead, we are using the word-to-vec code without making any modification. Okay, if you like, you can read the paper for fast text, and let me show you actually fast text paper. It is here. So it is by Mikalo. Mikalo is one of the authors of that original word-to-vec paper. So this guy. Okay, let me download the paper and show you the main formulation. Okay. To calculate the similarity between two words, W and C, C is the center word, remember, you get all the syllables of this W and multiply the vectors of that syllable with the VC. The VC is the vector for the center word. Okay, so this is the main formula for the similarity. Okay, this guy here, since it is written for generic language, they don't use syllables. Okay, they use the for example, for the word where, they have WH, WHE, HER, ERE, and RE. Okay, so this is like three letter combinations of the whole word. Okay, in English they don't have like the hece system. They don't have the hece system in English. In Turkish we have it, so it's kind of our. Without doing the syllables in Turkish, we don't talk, we don't write, right? Even our talking stresses, talking rhythm is based on the syllables, right? When I say invention, it's like I am talking like in Turkish, like invention. It is not pronounced that way, invention. Okay, it is not separated in the syllables that way. Okay, but we talk that way. That's why we pronounce those kind of words that way. That's how they understand that we are Turkish. When you talk English in to somebody who is native language in English, they immediately understand that you are Turkish because you are kind of applying this heceleme system to your Turkish speech. Okay, good. Any questions about the homework? Your report is as important as the results, because without looking at your report I cannot understand what you did. And I'm going to select some of you to make a demo, online demo of your results. Yes.
Can I ask a question? So, between okula and gitmek there is going to be a space, but we are not going to consider it, right?
Well, I thought about it. If it makes your results better, I suggest you use it, yeah. Because otherwise, there would be no difference between the two words coming together, okula gitmek and okula and space gitmek, right? So if you like, you can use space as a different syllable. Okay, good. So, first homework. The second homework will be similar to this one, but it will be about using a data set like this one, but it will be about counting letters and syllables again under a different context. Good. Okay, let me go back to the lecture slides. So you are going to test your result in two ways: analogy and similarity. So those are the intrinsic evaluation. How about the extrinsic evaluation? What did we say about the extrinsic evaluation? We said that it is about using those vectors in a real world application. One of the real world application is the word sense disambiguity or word sense ambiguity. This word pike in English has lots of meanings, okay? If you look at the Webster and Pike Webster dictionary,
And the only pike is weapon.
what?
The only pike I know is a weapon.
I don't understand what you are saying. Say it louder, sorry.
The only pike I know about is a weapon.
Really? I didn't know about, yeah. For me, pike means road. Okay. So you are going to get at least 10 different meanings. Pike definition. These kind of things happen. So 1, 2, 9, okay? There are 9 definitions of pike. A sharp point or spike. Okay. A mountain or hill having a peaked summit. Oh, okay, Pike's Peak, yeah. So what else? Freshwater tawny, okay, it's a fish type. Anyway, pike, heavy spear. The one that I know is, okay, pike is a, okay, the sometimes graphs pike, the inflation pike, etc. Yeah, I remember that too. It's like pipe, railroad or railroad. I know this one. I mean, this is the first one that I remembered. Anyway, so there are many versions. There are many meanings of pike. So the thing is this: how should I know which meaning that I am using in this sentence? By the way, either word2vec or glow or the method I am telling you, they are going to assign the same vector to this word pike, whatever the meaning is. That's not a good thing actually, right? That's not a good thing because each meaning should have a different vector. So we are going to find it. So the word sense disambiguity problem is assigning one of these numbers, okay, from 1, 2, 3, 4, ... 9. Okay. Assigning one of these numbers to a word pike happening in a sentence. Take the sentence, find this word pike, and try to assign the correct number to that one. I know this pike means a type of road. I know this pike means to kill or pierce with a pike. Okay? So that's word sense disambiguation example. Okay? So we could use it there, but before that, maybe I can run this algorithm to separate the meanings of pikes or jaguars. For example, here, idea the cluster word windows around words. Okay, and retrain with each word assignment to multiple different clustered bank to and etc. So it's kind of this. For each occurrence of bank, for example, try to give it a new name, bank 1, bank 2, bank 3, and then after you run your word2vec, do this clustering, and as you see, one of the meanings of bank is with transaction, finance, banking, and laundering. Okay, the other meaning of bank is is this one. What is gap, canal, plateau, territory? Remember the banks of a river? Okay, how many meanings of banks do you know? One is the financial bank with the money. The other one is the bank in the parks that we sit on. The other one is the The river, the size of the river that are with a slope, right? That's the bank too. What else? To bank is something to guarantee something. It's a verb actually. So this is the second one. Do we have the third one? No. What else? What else? Yeah, this Jaguar. One meaning is here. I think there is a company named Jaguar. I don't know. Oh, no, no, no. Jaguar is the name of an operating system for Apple. Is that correct?
They have some big operating systems problems. They have leopards, no leopard, maybe they have Jaguar.
I don't know. What is Jaguar then? I mean, it has something to do with the software. I didn't remember. The other one is
Okay.
Jaguar is a, I think, musical instrument. Jaguar. And the other one is car Jaguar, the brand name Jaguar. And I think there should be a Jaguar that has animal Jaguar here. Yeah. So in this case, I have 4 different vectors for the word Jaguar. Okay. Another guy came up with this idea. He said that I am going to explain this pike with this formula, superposition of different meanings. It has, let's say, 3 meanings. The word pike itself is, okay, weighted average of these 3 meanings. Okay, and alpha 1 is just f1 over these numbers. So you assign a vector first to the pike, then you try to separate into different meanings. And they are using some idea from sparse coding. Sparse coding is kind of an, let me try to very superficially define it this way. Sparse coding is representing your data in another world, in another space, which is way sparser than the original one. You don't compress it, you make it sparser, but you make your data more unique. So they are using the idea from sparse coding, and they can come up with these kind of, okay, tie. With the tie, you have many meanings again. The one, when you say tie, I always associate it with clothing, right? Trouser, blouse, waistcoat, skirt, etc. There is another meaning about tie.
Nobody does.
Okay, there is another meaning about tie, which is about tying something, tying the wires and etc. Okay, another one is tied scores, draw, right? It's this one. So these are all found automatically using this idea. Okay, good. So this is kind of a real world application of the word vectors, how they are doing it. Other real world applications are, for example, you can do this. Let's say I have a sentence. I have these companies, okay, for example, I wrote a comment about Gebze Technical University today, okay, and this is my comment on Twitter, I love GTU, okay. So my task is to classify this sentence into, is this a positive sentence, a negative sentence, or a neutral sentence? How am I going to do that? But I think I'm out of my time, right? I need to take a break. Okay, let me stop here. And when we come back, we will try to classify this sentence into negative, positive, and neutral using the word vectors. Let's be here around 15:35.
Hocam ben yazdım sanıyordum ama herhalde
Efendim?
Telefondan yazarken falan karıştı herhalde. Bu liste için. O zaman ben bu haftayı saymayayım mı sayarken?
Sayma. Ya bu derse gelmek niye bu kadar zor arkadaşlar ya? Herkes böyle parmak hesabı ders sayıyor ama. Alınıyorum ha. Ben de parmak hazırlık yapıyorum. Evet. Karıştırmış mı yoksa silmiş mi? Karıştırmış mı silmiş mi?
Mizah cihazı nerede biliyor musunuz? Mizah cihazını buldun mu?
Hayır, imzaladık onu. Ne zaman geldin sen?
İlk dersi kaçırdım. İkinci derste buradaydım da.
İmzalattım onu ya, daha tekrar dağıtamam şimdi. İsmin var mıydı?
İsmim vardı içeride de.
Okay, so we are going to look at this example. Let's try to separate this into two classes, either positive or negative, so that I can use this simple SVM stuff. So what am I going to do now? This one was a vector v1, v2, and v3. The simplest approach is just add them together and you get the vector for the sentence vs. Okay? So I have a vector for the whole sentence, and if I simplify this decision into two-dimensional vectors, of course I know that it's 300 dimensional, but just for the sake of example, let's take just two dimensions, first two dimensions, d1 and d2. Okay, if I draw it on this board, it will be, these are positives, okay, positives, and these are negatives. Okay, a line like this will divide this plane into two. As you see, I am making some mistakes, like one mistake here and the other one is here. You don't expect to perform 100% for these kind of cases. So it's a very simple approach to do this classification. This is called sentiment analysis. Okay, sentiment analysis. And it is done very frequently on this kind of social media sentences. It's a very valuable application, because maybe for Gebze Technical University you don't get many tweets or the social media stuff, but for large corporations such as Turkcell, I am sure they are getting hundreds of messages. They are talking about them. Some of them likes it, some of them don't like it. And if these numbers are getting larger, for example, people are being more and more critical about one company, the CEO has to know about it, or people are posting positive messages all the time, so they did something right. In that case, of course, I like to know about that too. Good. Okay. So this is how you are going to use your word vectors in real life application. Again, a simple real life application. Okay, any questions? Yeah.
The only part of that sentence is important, the love, the verb part.
Yeah.
But we are not considering it, we are considering all of it.
Yeah, because if I am going to go into detail of this sentence, I am going to skip this part and that kind of stuff. That will be more difficult, and I have to make decisions. Maybe I can factor out the stop words like the I, and, of, etc. Right? Maybe I can do that. Other than that, maybe I shouldn't do that much interpretation. For example, I mean, you might wonder, how is this going to differentiate I do love GTU from I do not love GTU, sorry. Not word has a word vector, okay. I mean, this one has I do not love GTU, and I do love GTU not has exactly the same word sentence vector, right? Because order is not important for the addition. So how is that possible that I can differentiate between these two? Well, for those kind of cases, this most simplest way of approaching the problem doesn't work. For those kind of cases, of course, we have more advanced techniques such as the RNNs, recurrent neural networks. They pay attention to the order of the words too. But we don't know how that. I mean, I'm trying to show you the most stupid, simplest technique that we can use. Okay. Good. So let's move on. I will not talk about these. Maybe they will come later. For now, I like to go a little bit classical and go back to chapter number 2 of the original book, finite state machines, and I will introduce the finite state machines to you. And maybe you know some of these concepts from the algorithms class or some other classes that you took before. It will be some repetition maybe, but I will try to be quick on this one. Okay, finite state methods. Okay, we keep using these regular expressions. Okay, regular expressions for doing lots of stuff like making a search, okay, grabbing something and etc. Here are some examples for the regular expressions. This means find me the word the, okay. It's not the word, I shouldn't say word, okay. Find me the occurrence of THE letters, one after the other, okay. That's the meaning of it, right? How about this one? What does this one say as a regular expression?
There, but the T can be capitalized.
It is the same thing, but we can match both the capitalized the and the small case letter the. How about this one? What is the difference between this one and that one?
A whole one there, so nothing before, nothing after.
You shouldn't say nothing. You should say maybe the white characters.
White space.
Yeah, white characters. Okay, white spaces before the and after the. Okay, so for example, the first one can match this one, and this one, right? The first one can match this one and this one and this one. I mean, it is doing whatever it is told to. It is matching THE characters wherever they happen. Okay, so it is matching this one, and this one. Okay, but the second one will match. I guess. Second one will not match any of, well, second one will match all of them, right? Again, all of them. But the first one will not match this one, right? The first one will not match this one because T is a capital letter now. Okay. Third one is the better one. It matches the small case the or the capital the, and it needs that white space before that. Okay. So this is just a simple example of the regular expressions. Why am I talking about the regular expressions? Because regular expressions are going to be our main method to explain the morphology, that is the structure of the words, and we are going to look at it. Now I'm not going to talk about letters about much, so it's going to be about finite state automata, okay? Those kind of regular expressions can be viewed as a textual way of specifying structure of finite state automata, and finite state automata will be our basic tools to study the structure of the words, or it is called morphology. Okay, morphology is the study of the structure of the words. Okay, syntax depends on the morphology of the words, but syntax is not just morphology. Syntax has rules about the order of the words too. Okay. With the morphology always, okay, as always, there is ambiguity. What did we say? In all the phases of natural language processing steps, we have the ambiguity, and of course, we have the ambiguity in morphology too. For example, when you analyze this word, Turkish word masalı, it has it has many meanings. One of them is the iyilik eki. Okay. This is about story plus I. Okay. Masalı. Onun masalı, bunun masalı, etc. Or we are talking about the object masa, table. Okay. With the table, you add this li suffix, and it becomes another noun, masalı. Okay, or sometimes adjective too. So morphology is not a single way of. There is no single way of analyzing words, and in case of ambiguity, there are many alternatives to it, and we are going to look at how the things work with this morphological analysis of the words. Okay, but before doing that, let's forget about Turkish or English. Let's go to a much simpler language of sheep language, kuzu dili. Okay, sheep language is very simple. It says that my words are like always this. Each word in English, you know, the sheep makes the sound ba, okay, not me in Turkish, right? It starts with B-A-A, right? And you can repeat this A as many times, at least once, as many times as you like, but each sheep word ends with an exclamation mark. Okay, so this is the regular explanation. You know the meaning of, what is the meaning of star? Star means
Zero or more.
zero or more. This means one or more, right? So this means every time I make a sheep language word, it has to start with a B, then A, then another A, then I can repeat this A as many times as I like, but at the end there should be an exclamation mark. If I represent the same thing with the finite state automata graphical way of showing things, okay, I start from this Q0, okay, state 0, with a B I go to Q1, with an A Q2, with a Q3, then I can stay in Q3 as long as I have A's, but at the end when I receive this exclamation mark, I am at the final state, which is the except state. So this is a very simple finite automata that analyzes any sheep language word. Okay, it is enough. It turns out that many human languages, especially languages like English, where the morphology is not that difficult, these finite state machines, these finite state automata should be sufficient to make this kind of analysis. Okay, and this language is very simple. This sheep language, it is this, right? There is no ambiguity in it actually. Okay, there is no ambiguity. It is always the same analysis. Okay, sheep finite state automata, it has 5 states. This is the start state. This is the final and except state. I have only 3 letters in my alphabet, B, A, and exclamation mark. And it has 5 transitions, that's it. Okay, that's it. You might say that this is the only way to explain, to express, to analyze the sheep language words, okay? The answer is no. There might be other cases. For example, this one. This one is exactly equivalent to this one. These two are equivalent. Okay? This one and this one except exactly the same set of sheep words. Okay? If you okay, there is a B, there is an A, another A, and I am finished, or I can do this and this. The problem here, and I shouldn't say maybe problem, maybe you should notice something here. When you are at Q2, when you get another A, should I stay at Q2 or should I go to Q3? So A will take me either to Q3 or to Q2, okay? I cannot make a decision by looking at A, but previously I didn't have this problem, okay? A will definitely take me to Q3, then Q2, then Q3. Another A will keep me at Q3, and if I get an exclamation mark, I am at Q4. Here, the situation is a little bit different. This is a deterministic finite state automata, deterministic, and this one is a non-deterministic finite state automata. Okay. Okay, both of them can explain the same language, deterministic or non-deterministic. Why is this why this is not deterministic? This is non-deterministic because when I'm at Q2, I don't know to go to Q3 or stay at Q2 when I see an A. Okay. So we'll talk about this a little bit more later. More formally, this is how you define a finite state automata. 5 things. Set of states. I have 1, 2, 3, 4, 5 states. Finite alphabet. What is my alphabet? Alphabet is A, B, and exclamation mark in this case. Start state is Q0. Okay. Set of, there is only a single start state, Q0. There might be one or more accept and final states. In this case, I have only one, which is shown with this double circle. Okay. And there is a transition function that maps state alphabet pairs to new states. Transition function. So 5 things define a finite state automata. Okay. Let me skip these. This is a more serious example. A finite state automata to recognize dollars and cents in English. Okay. From $0 to up to $99, right? $99.99. If you like to say $99.99, here it is, okay? From Q0, this is the start state, $99, and then after that, 99 cents. Okay, so I can recognize this. Okay, or you can $40.39. If you see this, you feed this to finite state automata. If you end up in this state or in this state, see, either Q4 or Q7 is final. You will recognize this. Okay, dollars and cents. Very simple finite state automata, but it is enough to explain this dollars and cents expressions in this case. Okay, let me skip this part. We are after recognition. I mean, when somebody, for example, if somebody says, is this a sheep word? I can run my finite state automata and I say yes or no. This is good, but usually this is not enough, because other than the recognizing, sometimes I need to know how I recognize this and the structure of the word itself. Remember this one? When I show you this word masalı, is this a Turkish word? Morphologically sound Turkish word? Yes, it is, but tell me how you recognize it. I recognize it this way. This is the root word. Okay, this is the noun. Plus I have this accusative ihali. Okay, suffix. So I know that I recognize it because of this root word. There might be other cases of other ways of recognizing that too. And in fact, let me show you one. There is one nice, very fast Turkish TR morph, okay? Turkish online word analyzer, and I think I run this. It doesn't work very well. It just keep repeating the same thing sometimes. I write masalı here. It said that, okay, masal is the root word. It's a noun. Then
Person 3.
then I am talking about the third person singular. Okay, third person singular suffix. So let me use this in a masalı okudum. Okay, masalı okudum. How about this one? This is the accusative that belongs to something, right? Possession, no. This is just opposite. This is possess. Let me go to the paper itself. I click on it. No, don't come back. Okay, let me do this. Open it in a new segment. Okay, so this is the manual. This is the paper itself. This guy, he did this, and it's a very valuable tool actually for us. And these are the, where are my noun? Yeah, okay. These are the noun inflections. Possessives, and this is, I think it was this one, right? Third person singular. P3S, right? This is P3S, yes, okay. This is the possession, iyilik 2. Onun masalı. Onun masalı güzelmiş belki, okay? How about this accusative? Masalı okudum. This is the accusative one, okay? This is the accusative one. Do I have the accusative? Yeah, here it is. Accusative, okay? There's the cases. İsmin ihali, ehalide, ehaliden hali, right? Those are the cases of the names. So you can look at this one, and there are many other. For example, masal is a noun. Again, this is again iyilik 2. Then masallı. I make a verb out of it. Well, how do you make a masalı? Nasıl masalı? Sometimes you use the verb, noun as a verb. Bu ev masalı. When you say bu ev masalı, just and after that dot, that becomes a verb, and it is for present tense and third person. I guess that's what it's trying to do. Sometimes we don't use those kind of morphological meanings, morphological analysis for the meaningful sentences, but the grammar makes it possible for you. Oh, okay. So this is the third meaning. Li suffix to make a noun an adjective, right? So when you say masalı ev, masalı in that case is an adjective, right? It is not a noun anymore. So it is different from the first two. So as you see, there are many different morphological ways of analyzing this word, this Turkish word, and you can get some of them from here. Anyway, like for example, this one is just it's going to be, I guess, just one. Did it work? Yeah, okay. Git is a verb, imperative, okay, second person singular, just an imperative word, emir, okay. But when I say giriş, okay, many different meanings. Git is the verb, and there is another suffix that makes it a noun, from the noun I can make it a verb again. I cannot come up with a sentence with this one. Gidiş. I don't know what this one is. YIS. So I need to go to the manual and look it up. Okay. So play with this one. Its name is TR morph. Okay. Or better yet, I am going to put this in the how can I get the, okay, here it is. Go to the chat and put it in there. Play with this one. It says my network quality is bad. Do you guys hear me okay? Online people?
Yes, sir, we are hearing you. There's no problem.
Okay. So, go back to the slides. So, when you do the recognition, it is not enough sometimes to say that muscle is a Turkish word, is right? I need to know its structure, morphological analysis. So, recognition by itself is not enough. We need to do the analysis too, and that's called morphological analysis. Okay. So recognition with a tape. I am going to skip these, okay, but I can give you this algorithm. This algorithm, D recognize. D means deterministic recognize. It takes an input and it takes the machine, okay, finite state machine itself. It returns either accept or reject. So this is for recognition. It doesn't give me any structure to the stuff. So it keeps reading the tape, the input tape, this one. It keeps reading it. Every time it reads it, it updates its state, okay, and it makes these transitions. When the tape ends, if I don't have anything else, it either produces accept or reject, okay. So there are two things that you can get out of these derecognize. It is either accept or reject. Okay? That's it. Let's look at this. When does the accept happen? If end of the input has been reached, if the current state is an accept, then it is accept. If end of the tape is reached, if the current state is not an accept, then it is reject, right? Let's look at this one. This will read A, B, O. At the beginning, if it reads an A for the sheep language, it cannot write. It cannot continue. Okay, so it will reject it. But which we reject is going to be? Is it this one or that one? Green reject or the blue reject? So my input is B, A, B, A, and B. Remember my sheep language? It was like B, A plus this. Of course, I am going to reject this, but which reject is that? This one or this one? Blue or green? It's going to be blue. Why? Because at the beginning, I cannot, when I see this A, I am at state Q0. There is no transition to anything at state Q0. Okay, here it is. For state Q0, I am expecting only B's. There is no A. So this is a reject. This is a reject. Okay? It's a reject. Or like this one, Q0, it's a reject. So that's one reject. The other reject is this one. I am done with the tape. I read all the input. I ended up in a non-final state. Okay? Well, in that case, I am rejecting this again. So this derecognize, its job is only to recognize stuff. As I said before, this is important, of course, but This is not the only thing that we want from the morphological analysis. We also want to see the structure of the words too. That's called the morphological parsing and morphological analysis. We talked about the ambiguity before. Okay, good. So recognition as a search, I will skip this one. I don't want to spend much time on this one. Let's talk about this one. As we said before, deterministic finite state automata and non-deterministic finite state automata. Those are two different things. Which one is more powerful, do you think? Which one has more expression power? What kind of things that I can say with the non-deterministic that is not possible with the deterministic? Can you think of any example? Or vice versa? The answer is no, there is no difference between them. So whatever you can do with a non-deterministic automata, you can do it with the deterministic automata. So they are theoretically they are equivalent in terms of processing power or their capabilities. We know that. But then why do we have this? And we'll talk about it later. These are more convenient for humans to explain stuff, and we will talk about it. So the problem here is this. When I get this A, am I going to stay at Q2 or am I going to go to Q3? And sometimes if I follow this Q3, I don't see this question mark, I have to come back and follow the other route. So there is a trial here. In this case, there is no trial. This is easy to execute. This is not that easy to execute. This is good for humans to write stuff. Okay? And there is another form of non-determinism. This epsilon transitions or empty transitions. You see there is an empty transition. To go to from Q3 to Q2, I don't need to read any inputs. By reading nothing, I can go from Q3 to Q2, no problem. So this one and this one is equivalent, which is equivalent to this one. And another way of making non-deterministic finite state automata. Okay. Okay, as I said before, non-deterministic machines can be converted. Okay. That means that they have the same power. Non-deterministic machines are not more powerful than deterministic in terms of languages that they can accept. Okay, so how do you do the non-deterministic recognition? So you just build a deterministic machine out of that grammar, non-deterministic grammar, and run the deterministic one. That's it. So your maybe grammar, your non-deterministic machine will be larger than the non-deterministic one, but it will work. But again, I am going to skip these. This is again a search example. Let's look at this one actually. This is a valid sheep word, right? Say yes. Yes. Okay, thank you. So let's try to run this tape, this input, through this non-deterministic finite state automata. Okay. So I started here. My state is Q0. And from Q0, if I read a B, I go to Q1. So I did that, okay? So at step 2, I am here at this position. I am at state Q1, and I am going to read this A. When I read this Q1, this A, I will go to Q2, okay? Let's do that. Now I am at Q2. I am reading an A. I have two options. I can go to Q3 or I can stay at Q2. Which one am I going to do? Should I go to Q3 or should I stay at Q2?
Q2.
Why?
For
because there is another way you are looking at it. But I mean, this is simple enough for us to say it, but how do you know without going to the end and making that decision? You cannot know that, right? I mean, you have to try both ways. So let's try one way, okay? Here, I choose to go to Q3, okay, by reading this A. Now I am at Q3, and I am reading another A. There is no way that I can continue at Q3. What does that mean? That means that I cannot continue this path. Am I going to reject this string now? The answer is, of course I should not reject, because this is a valid word, right? I should not reject it. So what am I going to do? I will backtrack, because I did not try all the paths. Now I'm going to try the other path, which is okay, which is this. Instead of going Q2, I am going to Q3. Q3, I am going to Q2. Okay. After Q2, I can read it again, but again I am going to ask the same question. Should I now, after reading this, should I go to Q3 and Q3 or Q2? Two options again. Q2 or Q3. But in this case, the smart decision is going to Q3, but still I don't know that. I have to try both of them. Okay. I try to go to Q3, and after Q3, I can get the exclamation mark, and I am done. Okay, so this is my path. I could have gone the other way here, Q2. Okay, once I find this path, I say that, okay, I recognize this one. So this is more expensive than doing the deterministic approach. In deterministic approach, you don't have to go back and try this stuff. You just try it. If it works, works. Otherwise, you immediately say that it is done. So this is more expensive to try. But again, as I said before, non-deterministic finite state automata are better for humans to write stuff. And we are going to see why at the end of this chapter in a few slides, but I'm not sure if I can make it. Okay, key points. Yeah, well, I'm going to. Okay. Why bother? Non-determinism doesn't get us more formal power, but it causes headaches. So why bother? Because it is more natural, understandable solutions for humans. What do I mean by that? Okay, by the compositional machines. Let's say I have two finite state automata, one for sheep language, the other one is for chicken language. Okay. For the sheep language, I have only BAA stuff. For the chicken language, the alphabet is a little bit different and the words are a little bit different. And I like to come up with a new language that combines these two. Okay. Any word from the chicken word or the sheep word, I can recognize them. So how am I going to do this? I am going to do this very simple. It's called union. Finite state automata 1 is here. Automata 2 is here. I am going to add one pseudo, okay, fake start state and fake final state. And I am going to connect these to these finite state automata using these empty transitions or epsilon transitions. Okay. This is a deterministic finite state automata, and this one too, but this whole thing is a non-deterministic. But it makes it very easy for me to see and to understand what I am doing here, right? So this is just a union of two languages by making use of finite state automata. I could have come up with a deterministic finite state automata for these two languages at the same time, but it would have been much more difficult to show it. Okay. Similarly, I can do concatenation. After each sheep sound, I need a chicken sound. This is how you do it. Again, I made a non-deterministic finite state automata. Okay. Another one is Negation. You know actually these rules, right? How do you negate a language? What does the negation mean? All the words that you recognize becomes invalid words, and all the words that you reject becomes acceptable words. That's called negation. And this is how you do the negation. Construct a machine M2 to accept all the string not accepted by a machine M1. Okay, so this is what you do. Invert all the accept and not accept states in M1. Invert all the accepts to not accepts, not accepts to accepts. Okay, this will be your new negation machine, and that's it for the negation. The interesting thing is the intersection. Okay, intersection uses this idea. What's an intersection of two languages? Two languages are accepting strings. I like to have a finite state automata that accepts only the common words. This is what you do. A intersect B. So this is what they do. Take the negation of A, take the negation of B, and run this union operation that I showed you before, and take the negation of the final stuff. Okay, so that's called the intersection. So you in doing this intersection, negation, concatenation, and union with the non-deterministic machines is very easy. That's why we like to work with non-deterministic finite state automata. Okay? Good. Any questions? Any questions about today's finite state automata and regular expressions? Next week I will continue this discussion, and then we will talk about how we are using this technique to do the morphological analysis of English first, and we will refer to Turkish from time to time. Okay. Good. Read your book, chapter number 2 or 3 maybe. 2 and 3, which is about morphology. And we will continue our discussion. Okay? I will see you next week.